Hello, so up to now, we've been assuming that we get given some data, imagining we get given some data, and we just want to try and get a feel for that data. And the first way that we looked at how we can get a feel for that data is by looking at this thing called an average. Now, an average is sometimes called central tendency, because if you think, if something moves towards a particular value, we say it tends towards a particular value, hence why we call it tendency. And if you think about the three types of averages that we can have the mean, we can have the median, but we can also have the mode. Okay, and in good data, so let's assume we have our data laid out in a list like this. So imagine all these points are just numbers in a list. And we've got them in ascending order, in order of size. And all we do, if we take an average, we should come out as a value which is somewhere near the middle. Hence why we call it a central tendency, because it sums out as a value which moves somewhere towards the middle. Okay, so it's just good to be aware of these other terms. But the good thing about an average, if you think an average is just a number which represents the data, a single number. If you like my analogy of a prime minister in a country, a prime minister represents the nation. Okay, much like an average will represent some whole data. But the trouble is with averages, which we looked in the last video, is that the data may have outliers in, which will obviously affect the mean. So because we're looking at the data as an overall, we may end up with the average not being the best representative of the data. So then we come on to look at this thing called spread. Now, spread is sometimes called measures of variation. You know, if something varies, then it has variation. So, you know, spread, variation, they're all kind of like words. They're all synonyms for each other. And we looked at, for example, the range, which is just highest takeaway lowest. So the value which, how far the data is spread out, okay? We also looked at this thing called the interquartile range, which is basically saying, right, we have our data, okay? And we take the lowest value, we take the highest value, and then we just split the data up into four. So we halve it, and then we halve it again. Okay, so we have the lowest value, we have the highest value, and then we just say, right, that one's Q1, that one's Q2, that one's Q3. And we talked about how to work those out in the last video. Okay, but look at this. If we now suddenly split the data up into four sections, we have a much better handle on the data. For example, if the majority of our data lied in the middle there, then because we split it up, we have much more control over the data. But look how many values we have as a result. So we have 1, 2, 3, 4. We have 5 values. 1, 2, 3, 4, 5 values instead of just the one number that we had up here. So that is a bit annoying. So what we want to try and do is have the same control over the data like we did with measures of spread, but we just want the single number as a result. Is there a way to combine those two qualities together? Well, yes, there is. And that's where variance and standard deviation comes in. So let's say we had data that looks like this. This is actual data which I've gone out and taken myself. I've gone out cycling and I've got a little bike computer and it measures my speed as I go through time. So this is me going through time along this axis, okay? And this is my speed being measured on this axis. So for example, at 20.42 minutes, I can see my speed was roughly about 20 odd miles an hour, okay? So this is just literally saying, you know, this is just literally what it's saying. And I've also got the white line plotted across here. It's just my average speed. And my average speed came out to be 18.2 miles per hour on this particular ride. So you can see what we're doing is you can see that my speed varied. You know, some points it was really, really high. Other points it was really, really low. So what I'm going to do then is I'm going to measure the distance of my speed at all my time points from the mean. So I'm going to measure it from this white line. So if I sort of say here, we've got a baby one here, we've got a small one below the line here, we've got another big one down here, big one here, small one down below the line here, big one above the line, and so on. And we basically move all the way through there. And we measure those distances, okay? And we're going to call them D1, D2, D3, D4, D5, etc., etc. We're going to go all the way through to Dn. So we're going to measure this final distance at the end, and we're going to call it Dn. Now, the only thing about this, so we measure those distances and then just take the mean of those distances, because the distances measure how spread out the data is. Then if we just take the mean of those data points, then we will just end up with a single value as a result. Great. But it's not just as simple as adding all these distances up and then dividing by the number which we've got. So let me just change the colour. So we just add all the distances up. So we add all the distances up, then we just divide by the number of distances that we've got. Not quite as simple as that, because look, we've got some distances above the mean, and then we've got some distances below the mean. So let's say, for example, that this distance here looks to be about 29. So the distance, so sorry, that's the height of this one here, and we're taking away about 18. So this distance here, the length of this arrow here, so the distance should be 29 minus 18, which works out to be about 11. So that's the distance above the line. But we've got this distance down here, which looks to be, I mean, this height down here looks to be about 7. Looks to be at 7. So we've got to do 18 minus 7 to work out the distance. So it works out to be about 11 here. But it's not positive 11, is it? Because it's below the line, so therefore we're going to have to call it negative 11. So if we just add these two distances, for example, let's say, just add these two distances for an example. So we've got 11 plus negative 11. That equals 0. So in other words, we get cancellations which occur. So it's not actually just as simple. So 0 divided by 2 is still going to be 0. Well, fairly obviously, the data does vary. It doesn't just stay exactly where we are. So we've got to try and do something to stop these cancellations from happening. And the inspiration for what we do comes from Pythagoras. So let's say, for example, we have a vector. We have a vector that goes off like this. Okay, and it starts at the origin. So let's say we start at 0, 0. Just for ease, it can start at any point, but let's just say for these, it starts at 0, 0. Okay, and then let's say it goes to, it goes to 2, 1. So the point, it goes from the origin to the point 2, 1. So what is the length of this vector? Right, much like we're working out the length of our distances in our data set, here we're just measuring the length of this vector. How do we do it? Well, we split it up into an x component and we split it up into a y component, okay, and we just form a nice little right angled triangle there. So how far do we move across? Well, we move across 2, okay, because we move from 2 minus 0, so that's 2 across. How far do we move up? Well, we move 1 up. Okay, so what is the length of this line? Well, it's going to be 2 squared plus 1 squared and then square root it. So it's going to be, so that's 4, 5. So it's going to be the square root of 5. So that's the length of this vector here. And it doesn't matter if it was a negative vector. So for example, if we have something like this. So again, we start from 0, 0. Okay, and we go from here to here. And we go down to, let's say this is still 2 across, but now we go negative 1 down. Well, what's the length of this vector? It should be the same vector, just in a different direction. Well, we're not bothered about the direction, but let's just verify it. So we go 2 across, so the x is still 2, but now the y, the y part is negative 1. So what's the length of this vector? Well, it's going to be 2 squared plus negative 1 squared. Then we take the square root of that. So 2 squared is 4, negative 1 squared is just 1. So it's 4 plus 1, so it's the square root of 5. So good. They do correspond. It's the same vector. Okay, and we're going to use exactly the same kind of principle here with our data up here. So we're going to square it to make sure they're all positive, first of all. So we're going to take all our distances, let's say D1, D2, D3, right the way through to dn, so all of our distances, okay, so all of our distances which we've measured, okay, and then we're going to square each one. We're going to square each one, and then we're going to add them all together. Like we did down here with our Pythagoras. We added them together. Okay, then we're going to take the mean of all those distances, because are you happy that if we square a value, it's still going to be positive, right? So negative 1 squared is going to be just 1, so it's always going to be positive if we square a negative value, okay. Then we're going to take the mean of those. So we've got n distances in total, so we're just going to divide through by n. And that will give us our mean. Okay, so we take all of our values and we just divide through by the number which we end up with, and that will give us our mean of all these distances. But then what we can do is we can square root all of that. So we can square root all of that, and that's how we find out the standard deviation. So there's two little concepts that we need to just familiarise ourselves with. So let me just write it out again. So the variance is just simply the step before the square root. So we just take d1 squared plus d2 squared plus right the way through to the final value, so dn squared, and then we just take the mean, okay? But then the standard deviation is just simply taking the square root of all of this, so d1 squared plus d2 squared plus right the way through to dn squared, over n. So we just simply can say that standard deviation is just the square root of the variance. Standard deviation is the square root of the variance.